Hello. In this video today, we're going to go over the polar regions of integration. And so the idea is that sometimes we're going to have certain integrands in our integrals that we can't actually integrate with any methods that we've learned so far. And so it will be helpful for us to be able to maybe switch our variables to a different sort of plane and see if that makes a difference. So in this particular problem, we have an integrand of cosine of the square root of x squared plus y squared, which I cannot integrate if I leave it in x and y. But I'm noticing that there is an x squared plus y squared function that's inside of the cosine, and that makes me think about circles. And it's really important, as you may have noticed in Calc 3, that we use our advantage with circles and what we can do with them. So we could come up with, let's see, in this particular problem, not only is the integrand got a circular relationship in it, and that's not the most important part. Really the most important part is that the region D is the top half of the disk with the center, the origin, and radius 5. So I need to come up with an equation for that, and an equation of the top half of a circle would be y equals a positive square root. If the radius is 5, then under the square root we'll have 25 minus x squared. So this y equals root 25 minus x squared, that models the graph that I have here. And I guess I could close up the domain along the x-axis. So with this particular domain, or for my region of integration, if I wanted to set up the integral, I could think of this as a type 1 region. And I would then decide that, okay, the lower bound for y is 0, and the upper bound is the equation of this circle, which is the square root of 25 minus x squared. I chose the positive square root because this is a circle above the x-axis, and so y is positive there. While y is going from 0 to the top half of the circle, x is traveling from minus 5 to positive 5. So I set this up, and now things are even worse. Like, not only can I not integrate this integrand, I'm looking at those bounds with the square root, and there's just nothing I can do here. So we're going to get nowhere with this setup. But what if we decide to recall polar coordinates that we learned in Calculus 2 and possibly in pre-calculus? So the polar coordinates say that x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is r squared. If we use this sort of transformation, we should be able to get ourselves a much, much nicer integral to work with. So let's see how that works. Now, if we were to work with this circle, we would have to figure out, like, what is my radius going to be and what is my angle going to do? And so we have to remember that the radius is a measurement of an arm. It's a radial arm, and it's always positioned with its start at the origin, and then it's an arm that swings around, and as it swings around, it arcs out a curve, okay, typically known as a circle. So r is positive. It is never negative. It is always a positive value. So we have a radius of 5. That means that we could let r go from 0 to 5. And since this is just the top half of the circle, the theta values that are being taken on are starting at 0 and going all the way to pi. And so we could use those for our bounds for our region of integration. And then if we were to fix our integrand, because that was also a problem, and it's got x's and y's, we need to get rid of the x's and y's. What ends up happening is we're taking cosine of the square root of x squared plus y squared, but x squared plus y squared is r squared. And if we square root that, we just get an r. So that is a much, much simpler function for us to integrate. In fact, we can actually do it, whereas before we couldn't do anything. So now we have to figure out the differential, because before the differential was dy dx, and we can't use dy dx because we're using r and theta. So we have to figure out, like, is this going to be dx dy equals dr d theta, or is there going to be a little something extra? Like, what's going on here? Well, it turns out we have this thing called the Jacobian. And the Jacobian is something that is used, it's a determinant. We've seen determinants before. The Jacobian is used when we have a transformation of variables and we need to figure out what our new differentials are going to be. It is also used for other applications, but that's how we're using it here. So what the Jacobian does is it's going to allow us to take, we're going to take, so as we can see right here, I've got j of r cosine theta. Whoops, that was previously my x. Okay, hold on, I'm trying to get my pen to work here. Having some hesitations. I'm going to pause this real quick. Okay, that worked. Okay, so the first coordinate was x and the second one was y. And now each of those are a function of two variables, r and theta. So the Jacobian says, across the first row of the determinant, put in the first partials of x. Well, since x is a function of two variables, we would need a first partial of x with respect to r and a first partial of x with respect to theta. Now the second variable goes in the second row, and it's also going to be first partials with respect to r and theta. So I calculate what those first partials are. For x, the first partial with respect to r is just cosine of theta, and I'm going to put in a dr. Okay, so we know like what that was. And then with the first partial with respect to theta, well, the derivative of cosine is negative sine, so we end up with negative r sine theta d theta. So that's my first row. Y is r sine theta. First partial with respect to r is sine of theta dr. First partial with respect to theta is r cosine theta d theta. So now that I've got those values in there, I go ahead and I take the determinant. Remember, upper left corner times lower right corner minus the lower left corner times the upper right corner. When I multiply all of those out, I notice that each of the terms has a dr d theta, and I notice that I can also factor out an r. So I'll factor out an r on the left, and I will factor out the dr d theta on the right. And we see that what's left behind is a cosine squared plus sine squared, which is just 1. And that's how we get the dA when we're in polar coordinates. dA is r dr d theta. You can also think of it as the pirate differential. You know, pirate would say r dr d theta. It's silly, but maybe it'll stick with you. All right, so now we can put it all together. I'm going to go from what we had before in rectangular coordinates with horrible bounds, a horrible integrand, and I'm going to switch to polar. My integrand is now cosine of r. My differential is r dr d theta. And then I've got my bounds. Theta goes from 0 to pi, and r goes from 0 to 5. That looks pretty nice. All right, so let's go ahead and do this. I'm going to write this out. We have the integral from 0 to pi, the integral from 0 to 5 of r cosine of r dr d theta. Well, unfortunately, there still is an integration by parts right here. So I'm going to go ahead and do an integration by parts. And with the integration by parts, I need to have a u and I need a dv. Since it's a polynomial and a cosine function, I'm going to let u be the polynomial part. Oh, hold on. Something funky's going on with my video here. Okay, let me try that one more time. This is my integration by parts. My integration by parts, I have u is going to be r, and dv is going to be, well, the other part, the cosine of r dr. Now remember, we're just focusing on the r part. We're not focusing on theta. Okay, so if u is r, then du is just dr. And if dv is cosine of r dr, then v is sine of r dr. And so if I recall, this is uv minus the integral of v du. That's integration by parts. So that'll give me r sine of r minus, hold on, my v should not have a dr, minus the integral of sine of r dr, which gives me r sine of r plus cosine of r. Okay, so we've got an integrand, we've got our antiderivative. We can go ahead and substitute that back into our integral. And I think I need to pause again. Okay, so this is equal to the integral from 0 to pi. That's going to be for the d theta. We'll do that next. And now we have found that we've got r sine of r plus cosine of r for the antiderivative with respect to r. The bounds are from 0 to 5, and then we have our d theta. Okay, I'm going to go ahead and evaluate 0 to pi. We get 5 sine of 5 plus cosine of 5 minus 0 minus cosine of 0. So that cosine of 0 is 1. It looks like everything here is just a constant. So we get the integral from 0 to pi of 5 sine of 5 plus cosine of 5 minus 1 d theta. So when I integrate with respect to theta, I'm just going to get this constant times theta. So we have 5 sine of 5 plus cosine of 5 minus 1 times theta, evaluated from 0 to pi. And when I evaluate that, the 0 has no contribution, so our final answer, we have a pi in there. 5 sine of 5 plus cosine of 5 minus 1 all times pi. So that made life doable, right? Or I guess life was always doable, but it made this integral doable. Let's see what else we need to keep in mind here. So a few things, and I already mentioned this, but these are so important. Turns out every time I switch tools, I'm having. So what we have to keep in mind here, number one, r is always positive. You start writing r as a negative, you're going to get your problem wrong. And is a major concept misunderstanding if you make that mistake. That's not a minor mistake, it is major. A radius is a radial arm. It sweeps out angles. It doesn't do anything else, okay? Theta goes from 0 to 2 pi, and that's the biggest interval that you can have for theta, and that's a full circle. Now, we could take any portion of a circle that's less than this, and it could have a different upper bound and possibly a different lower bound. Like we could go from minus pi halves to positive pi halves, right? So it is possible to have theta as a negative value. Like that would work, for example, if we were looking at the right half of a circle. Whoops, I'll need to change this tool to draw that. Let's see if it actually changes. It's going to take a moment. I'll talk it out first. Okay, so if we are looking at the right half of a circle, for example, the right half of a circle would start down at minus pi halves, and it would go up to positive pi halves. So we have to keep in mind that we can switch our theta around. It can be negative, but typically, so almost always, but really just typically, it's going in a domain from 0 to 2 pi. So here's my example. If this was the circle we were dealing with, then we would have theta going from minus pi halves to positive pi halves. Okay, so it's just one possibility. All right, let's do some examples. We're going to evaluate this integral by changing to polar coordinates first, and we are given the double integral of the arctangent of y over x dA. We are also, now this is an integral over r. We're calling our region r again instead of d, and it's kind of indicative of a polar region. And r is defined by the set of x, y values that satisfy a circle, kind of a circle, but it's the part of a circle that is between the radius of 1 and the radius of 2. Remember that a radius is the square root of the numbers that we see. So we're saying x squared plus y squared is stuck between 1 and 4. And then we're also given that y is between 0 and x. So we don't want to just take this and blindly substitute in r's and r cosine theta and r sine theta. We want to take this and draw the region, and then from the picture, we're going to decide what our r values are and what our theta values are. So I'm going to draw what it means to have a circle that is between 1 and 4. So I need to draw out my axes. And a circle with radius 1 is right here. Then we have a circle with radius 2. I'm drawing these with dashed lines just so I hopefully draw better circles. Okay, so we are talking about the region in between those two circles. That's like a donut, okay? Food is always a great explainer of regions of integration. Now, the other piece that we're given here is that y is going from 0 to x. So this means we have y equals x and y equals 0 and y equals x as functions on our graph. So we need to draw those. Y equals x bisects the first and third quadrants. Y equals 0 is the x-axis. So I'm going to have to pause again for this pen. Okay, so we need to have a bound down here on y equals 0, right? It's going all the way across, but our real region is just this like little sliver of the donut. It's like we're taking the donut and cutting it up into pieces so we can share it. So it's just right here. Now that region, I can see that my radius is going from 1 to 2. And if y equals x bisects the first quadrant, that means that it's going through at an angle of pi fourths. So it looks like theta starting at 0 and going up to pi fourths. That is a heck of a lot easier than going to the region as it's described in y and x and trying to just convert those all to polar. Draw a picture. Get your region from your picture, okay? Every now and then we will use the bounds if the picture doesn't make it blatantly obvious, but we don't like try for that first. All right, we also need to fix the integrand. So these are our bounds. And the integrand is arctan of y over x, but we have to remember that we're going to change y to r sine theta. So let's write that out. Arctan of r sine of theta, and x is now r cosine of theta. Those r's are going to divide out. We have arctan of sine of theta over cosine of theta. And then we need to remember that sine over cosine is tangent. So we are taking arctan of tangent of theta. And the arctan and the tangent undo each other completely. They are inverse functions. And so this is just theta that's left behind. All right, it looks like we're ready. So our double integral over r of arctan of y over x is equal to the integral from 0 to pi over 4, that's for my theta, the integral from 1 to 2, that's for my r. My integrand is now just theta. dA, we have to remember, is r dr d theta. Okay. Now, I want to do a little trick here because I think at some point I've got to introduce it. And I always hesitate to introduce it because it does get abused. But what I'm seeing here is that I have functions theta and r which are separable. What that means is that they are written as products of each other and we can factor them away from each other. And so this is not always something that can happen, but it happens to be able to happen now. So I can rewrite my integral as the integral from 0 to pi over 4 of theta d theta times the integral from 1 to 2 of r dr. This only works because the r and the theta were separable. If we cannot factor them so that they're completely separate in a product, then we cannot do this. Normally, the double integral of a product is not the product of single integrals. Only sometimes. So just like kind of a side note, this is only possible because the integrand could be rewritten, and I'll state what I mean by that. So we had an f of theta, or f of r theta. We were able to rewrite it as h of r times g of theta. That's what we mean when we say that a multivariate function is separable. Okay, so now that I've done that, let's get off of that. I can integrate these simultaneously, and that just speeds up the process, and it's a little less writing. So the first one, we have the integral of theta. The antiderivative is 1/2 theta squared from 0 to pi over 4. We're going to multiply that with the other one. The antiderivative of r is 1/2 r squared. We're evaluating that from 1 to 2. We go ahead and do the evaluation. We get 1/2 times pi over 4 squared is pi squared over 16, and then minus 0. And then my other one, I have 1/2 times 2 squared is 4 minus 1 squared, which is 1. And so I get 3/4 times pi squared over 16. That's going to give me 3 pi squared over 64 for a final answer. Okay, so there was a lot going on there. First, there was changing to polar coordinates and getting the right bounds and getting our integrand to be right. And then next was this whole new concept of being able to rewrite a double integral as a product of single integrals. Just be very, very, very careful when you use that. All right, here's another example. We're going to use polar coordinates to set up the integral that would calculate the volume of the region inside the sphere, x squared plus y squared plus z squared equals 16, and outside the cylinder, x squared plus y squared equals 4. So I'm going to go with food again. If we have something round, like an apple, picture a perfectly round apple, and we have a core. It's like a cylindrical knife that can cut out the core of the apple. So we core the apple and we take the core out. What's left is the apple without its core. We want to find the volume of that. Okay, that's what we're after here. I can try to draw it. Let's see how that comes out. So here's my apple, perfectly round. Not really. Put a belt on it so it actually looks like it's something round. I'm going to switch my color. Now I'm going to draw a sphere. I'm sorry, not a sphere, a cylinder. I'm going to draw it slightly above and below. And I'm going to give it a belt too so that we can kind of see that three-dimensional side of this. And then I'll put some axes on this. Okay, we want the region that is outside of the cylinder, but inside of the sphere. Okay, so we're going to core our apple, and then we're going to eat what's left. What this looks like if we project this into 2D is, well, let's see, the cylinder has a radius of 2, and the sphere has a radius of 4. It's 1, 2, 3, 4, 1, 2, 3, 4, and so on. All right, we're going to draw the cylinder radius first. Okay, and then we're going to draw the sphere radius second. You know what this is looking like? This is exactly like the previous problem. We have a donut. So in 2D, we're seeing a donut, which makes sense. If we were to take little slices of a cored apple, they would all have a donut shape as well. Okay, now we are not restricting ourselves to any particular octant. So this region tells me that my r, my radius, is starting at 2 and going up to 4, while theta is taking a whole trip around from 0 to 2 pi. Okay, now we want the volume of the entire region inside the sphere. So that's the top and the bottom. We need to be aware that when we examine a sphere, and we solve for z, we first have z squared is 16 minus x squared minus y squared. We take the square root and we get plus and minus the square root of 16 minus x squared minus y squared. Now an integrand is technically going to be the top z function minus the bottom z function. The top of our sphere is the positive square root. The bottom of our sphere is the negative square root. So that means we're looking at the positive square root of 16 minus x squared minus y squared minus the negative square root of 16 minus x squared minus y squared, which means that we have 2 times the square root of 16 minus x squared minus y squared. Okay? In polar, because we are going to polar after all, this is equal to 2 times the square root of 16 minus r squared. You have to remember, anytime you see that x squared plus y squared, it could even be hiding as a minus x squared minus y squared. Replace it with r squared. Okay, so then the last part is our dA will be r dr d theta. Okay, I think we have everything we need. We can go ahead and set up our volume. The volume will be the double integral. I'll leave the outer integral for my theta, that's 0 to 2 pi. My inner integral is for r, it goes from 2 to 4. My integrand is 2 square root of 16 minus r squared. My differential is r dr d theta. Okay, I can imagine that r over next to the 2 and actually just go ahead and write it. 0 to 2 pi, 2 to 4, 2r square root 16 minus r squared dr d theta. So it looks like I have a u sub. I'm going to go ahead and work on my u sub over here. If I let u be the stuff under the radical, that's the 16 minus r squared, it's going to make my life a lot easier. So du will then be minus 2r dr, which is not quite what we have over there. Let's divide both sides by negative. So negative du will replace 2r dr. All right, so I'll walk through my u sub, put the negative outside. The 2r dr is replaced. I have the square root of u, which is u to the 1/2, and then a du. Integrating this gives me a negative 2/3 u to the 3/2. Okay, now I can go ahead and do that. So this is equal to, back to my original, 0 to 2 pi. My antiderivative is negative 2/3 times 16 minus r squared raised to the 3/2 power, going from 2 to 4. After I'm done with that, then I can deal with d theta. So I have to evaluate. This gives me the integral from 0 to 2 pi of, actually I can write this as a negative 2/3, and then inside, when I evaluate at 4, I get 16 minus 4 squared, so it's going to be a 0 to the 3/2. Minus, when I evaluate at 2, I get 16 minus 2 squared, which is 12. So I have 12 to the 3/2. And then I have my d theta. This number inside is all constant. There, it's just a constant. It's not, there's no function in there. So when I integrate, I'm just going to get a theta. Cleaning up my constant though, the integral from 0 to 2 pi of positive 2 over 3 times, well, you know what, that 12 to the 3/2 can be rewritten as 12 square root of 12 d theta. Okay, go ahead and rewrite. I'm going to go ahead and find my antiderivative. So I have 24 square root 12 over 3 is theta from 0 to 2 pi, which is going to equal 48 pi square root 12 over 3, which simplifies to be 16 pi square root 12. Now I'm going to deal with that square root 12. The square root of 12 is 2 root 3. So this is 32 pi square root 3. Any one of these representations is fine, but the final one is actually simplified as much as we can. All right, I'm going to stop this right now and I will finish up with a part 2 for polar coordinates.